Okay. Um, so we didn't have lab last week, but we do have lab this week. Uh, and does anybody have any questions about the two homework problems? I'd be happy to go over one of those if anyone would like. Um, okay. That stuff can be a little tricky to think about, like how moving around the position equals zero in the positive direction and stuff, how it affects the graphs. Um, but anyways, if you have questions about that come up, please let me know. I mean, I'm sure everybody has the same questions as you. Uh, also, I assign these daily problems one time each, but the people who do well in this class will almost all do these problems multiple times, you know? And so it's now been a week or so since I assigned the first set of problems. I think that's a good time to go back when you can find time and do those problems again and make sure that those approaches are sticking. Okay, so doing these problems one time is probably not enough for most people to stick it in your brain. And if you take the time to do it a couple times, you're going to see the results from that in the tests and stuff. Okay, so redo the problems. Just because they're not assigned doesn't mean it's not helpful. All right. So we started talking about position. So the topic that we're in is 1D particle kinematics. Um, so particle means that we treat it like it exists at a single point, even though we don't assume it has zero mass. So remember that. Mass, we're always going to assume that these things have their normal mass. That doesn't come up yet. And then 1D means that we're thinking of it moving along a line. And last time I talked about the definition of position and the relationship between position and time and drawing position versus time graphs. So today I have to define velocity and acceleration. Um, so last time was position. This time I'm going to start by talking about velocity. And in everyday speech, velocity and speed are just synonyms. You use, like, if you use, say, speed in a paper, then the next time you say velocity, so it doesn't sound like you're repeating yourself. In physics, they're different things. So keep that in mind. So speed in physics is what it means in everyday speech. Velocity is a measure, so it measures how quickly the position is changing. And it has, think of it as like a speed, but with direction attached. Okay, so if you take a road trip to Iowa, your car says 60 miles an hour, your speedometer, as you head down to Iowa. And then on the way back, it says 60 miles an hour, even though you're going in the opposite direction. There's no direction attached to speed. Okay. Velocity, so this speed, whenever I give you a capital V, that's going to mean speed. It's like, because it's the absolute value of velocity. Lowercase v is velocity. And so the velocity v is plus or minus the speed. And the sign of the velocity tells you which direction the thing is moving, tells you the direction of motion. Okay, so when we're talking about one-dimensional motion, you always choose a positive direction, and that defines the negative direction too. And so then if the object is moving 60 miles an hour in the positive direction, the velocity is positive 60. If it's moving 60 miles an hour in the negative direction, the velocity is negative 60. Okay, so that's how the directional information is attached. So for example, so like with the Iowa example, if you called north your positive direction, then south would be your negative direction. And then while you were driving down south to Iowa, your velocity meter on your car would say negative 60 miles per hour. When you drove back, it would say positive 60 miles an hour. That's how the sign works. Okay. So if you have, let's say a car is moving on an incline, and let's say it's going this way at 30 meters per second, and let's say we've defined our positive direction to be this way, and our negative to be this way. What's the velocity? Well, the velocity is plus or minus the speed. And now you have to think about which way it's moving. In this case, it's moving in what we defined as the negative direction. So this is negative 30 meters per second. Okay. The units for velocity are the same as the units for speed. It's always units of length divided by units of time. And that means that the SI units are meters per second. Okay, last time we started talking about position versus time graphs. So now I want to talk about how you would recognize the direction that something's moving on a position versus time graph. Okay, so on a position versus time graph, the velocity at a chosen instant is the slope of the tangent line. If you're just trying to figure out the direction that something's moving, remember that this is a positive slope. This is zero slope. And this is a negative slope. Okay, so for example, let's say that you have you're looking at a position versus time graph that looks like this. Does P go on the vertical or horizontal axis? Vertical, perfect. And time is on the horizontal. And let's say that your position versus time graph looks like this. Okay. And let's say there are 3 points that we're going to think about, A, B, and C, 3 different instants. And the question is, what direction is the object moving at A, B, and C? First we have to figure out what the tangent line is at each one of these points. And we did that as some of the exercises in our lab activity last time we had lab. So a tangent line here at A, draw the 2 nearby points on the graph, draw the line through them, and that's the tangent line at A. And so at that point A, is that a positive, 0, or negative slope, that tangent line? Yep. So that's a positive slope. So velocity is positive. And that means it's moving in the positive direction. Now let's think about B, this point B. I'll draw the 2 nearby points on the graph, draw the line through them. Is the slope of that line positive, 0, or negative? 0, yep. So velocity is equal to 0. So velocity equals 0 means that it's not moving. So it's just sitting there wherever it is. And then for C, draw the 2 nearby points on the graph, draw the line through them. So that blue line, does that have a positive, 0, or negative slope? Negative. So the velocity is negative. And that means that at that instant, the object is moving in the negative direction. Okay, let's do another example, but this time we'll throw in, so all of this happened in Math World. I didn't tell you, like, this supposedly represents a physical motion in the real world, but I didn't show you any of that. So everything was just numbers, graphs. So now let's say that we have a position versus time graph that looks like this. And the point that we're interested in is right here. And say that this represents, so this graph is in Math World, but let's say that this represents in the real world a motion along an incline like this. Where we've already chosen, say, that positive is this way and negative is this way. Okay, so at this chosen point, at this chosen instant on the position versus time graph, which direction is the object moving in the real world? So what we're going to do is look at this position versus time graph, figure out the slope of the tangent line. So I'll draw the two nearby points. The tangent looks like this. Like you said, that has a positive slope. Okay, so V is positive, which means it's moving in the positive direction. Now we go over here to the real world. We know that it's moving in the direction we called positive. So that means that this is moving down the ramp this way. Any questions about that? I mean, I think this kind of stuff, largely it's just a matter of looking at it a bunch of times and sort of making it part of the way you naturally think about things. But remember, we're going to be looking always at graphs, mathematical stuff, and then that's always representing something about what's physically happening somewhere. Okay? Physically, what this graph is telling us is that at that instant, this object is moving down this ramp. So I guess I'll draw it again there. Okay, and now we have to talk about what acceleration is. So when I introduced velocity, I said velocity, where is it? Measures how quickly position is changing. And so if the position isn't changing, if something's just sitting there, the velocity is 0. Acceleration works that way, but with velocity. Acceleration measures how quickly velocity is changing. Bless you. Okay, so if velocity is 0, that means that the position is staying whatever it is, wherever the thing is. Okay, think about what this means. If the acceleration is 0, it means that the velocity is not changing at all. But it doesn't mean that the thing is staying still. It just means the velocity isn't changing. It could be negative 500. It's just staying negative 500. Okay. And so the first thing I want you to remember is that constant velocity and 0 acceleration mean the exact same thing. It's like two different ways of saying the same thing. There's something sort of funny coming up with acceleration when we get to two-dimensional motion. Most of the stuff, when we go from one dimension to two dimension, go from moving along a line to being free to move along a plane, the meaning stays pretty much the same. But this is one thing that's sort of fundamentally different. In 1D, acceleration always, non-zero acceleration, always means an object's speed changes. It just means an object speeds up or slows down. That's the only thing it can mean. In 2D, there's a new thing that doesn't exist in 1D. So acceleration in 2D can mean either one or both of these two things. First, speed change. But in 2D, it also can mean that the object is turning.
Rotation?
What?
Rotation? Is that
Yeah, I mean, I think you're probably thinking about it right, but what I call rotation is an object changing, like this is rotation, you know? And with particles, remember, that doesn't exist. So with particles, all you have is paths, and you don't know how the thing is facing, you know? So I'm just going to call it turning. It's moving, not going along a straight line. But in 1D, there's no such thing as turning. All you're doing is going back and forth along a line. Okay, so that's why, though, like you can feel acceleration. You feel it in your stomach, kind of, you know, like when an elevator starts to move just briefly, you feel that feeling in your stomach. It's the acceleration that you're feeling as the speed changes. And you also know that without the speed changing, you can have that same sensation like at, you know, on a roller coaster or whatever. You could, even if you're moving the exact same speed as you go around a sharp corner, you're accelerating because you're turning, you're changing directions. Okay, so like when, you know, the thing, I don't know if they still use this or whatever, they call it a centrifuge, I think, but they put the astronaut in the seat and then spin him around in a big circle to get him used to high G forces. They're not changing the speed of that thing once it gets up to full speed, but that person is feeling a lot of acceleration because they're turning really quickly. You know, they're turning, they're changing direction very dramatically. Okay, but we're in 1D, so for now, acceleration just means that the speed is changing. Okay, so now what does the sign of acceleration mean in 1D? And then we'll sort of extend this to 2D when we get there. So the sign of acceleration in 1D. Okay, well, if 1D acceleration always means the speed is changing, and you had to guess what positive and negative acceleration meant, I think most people would probably guess like, maybe positive acceleration means the thing is speeding up, and negative acceleration means it's slowing down. But it doesn't quite work that way, okay? Here is what the sign of acceleration means. If the velocity and the acceleration have the same sign, then the object is speeding up. And if the velocity and acceleration have opposite signs, then the object is slowing down. The units for acceleration are always units of length divided by units of time squared. And so the SI units are meters per second squared. Okay, with velocity, we talked about how you can sort of read the sign of the velocity if you're looking at a position versus time graph. Let's do the same thing with acceleration. So on a position versus time graph, the acceleration is shown by the concavity of the graph. So in which direction the graph is concave. So if the graph is part of a concave up curve like that, the acceleration is positive. If where you're looking at the graph is a line and it doesn't matter what the slope is, but if the dot that you're looking at, the instant you're looking at, is on a part of the graph that's aligned, then the acceleration is 0. And if the instant you're looking at is on a part of a concave down graph like that, that's a negative acceleration. And a lot of this stuff you're just going to have to come up with ways to remember on your own, but I can help you with the acceleration one. This guy has a positive attitude, and this guy has a negative attitude. So. Okay, so let's do an example. So I'm going to draw just a random position versus time graph. So let's say that represents the motion. And remember, this motion looks curved, but this is a representation of a one-dimensional motion. So this is just telling you how this object is moving back and forth along a line. Okay, the object isn't following a path like that. Okay, and let's call this point A and this point B. And I guess we might as well make let's think of this on the real world. So let's say in the real world, this represents a motion up and down, and let's say we've chosen our positive to be down and our negative to be up. So at A and B, let's figure out what direction the object is moving. And then let's figure out, is the object speeding up or slowing down? So at the point A, to figure out the direction the object's moving, we have to figure out the tangent line. So I'm going to draw the two nearby points on the graph, draw the line through them, and that's the tangent line. And is that a positive, 0, or negative slope?
Positive.
Positive. Okay, so it's moving in the positive direction. And is the positive direction in the real world up or down? Down, so this thing is moving down. And now let's think about the acceleration. At this point A, is that point on part of a concave up or concave down graph or on a line? It's concave down. So the acceleration is negative. The velocity and acceleration have opposite signs. So it's slowing down. So at this instant, this object is moving down and slowing down, you know, coming like braking or whatever. And now let's think of the same thing at B. A tangent line looks like this. So is the slope positive, 0, or negative? Negative, yep. The slope, yeah. So it's moving in the negative direction. Is that up or down? Up. Question? Anybody?
I thought you were asking if there was a positive acceleration.
Oh, okay, yeah. So that's next. So now is it concave up or concave down? Up. So acceleration here is positive. So again, this time velocity is negative, acceleration is positive. Velocity and acceleration have opposite signs. So again, it's slowing down. So in this case, it's moving up and slowing down. Anybody have any? Yeah.
So for the slope, as we determine the sign of the slope, that's determining in what direction in the real world it's moving. Like in terms
Yeah,
of positive or negative.
Right. Positive or negative just tells you whether it's moving positive or negative. And then if you have a picture of what positive and negative are in the real world, it tells you physically what direction it's moving. That's right. And sometimes you'll do problems where it'll never mention a relationship to the real world. And so all you can say is, like, in this case, it's moving in the positive direction, whatever that is.
Thank you.
Yeah. Any other questions right now? Okay. Well, so now we're finally going to talk about some calculations we can do. So now I'm going to introduce the constant acceleration equations. So we're going to be using these equations that are true whenever the acceleration is constant. And one thing I want to point out is there's no reason that something has to have constant acceleration. Accelerations can change over time just like anything else. And if you look at this graph, this problem we just were looking at, you can see that that's a negative acceleration for about the first half of the motion and then a positive acceleration after. Well, that means that it's not constant acceleration, you know, it's changing from negative to positive over time. But there are some important motions that do have constant acceleration. The most important one is stuff that's in free fall or projectile motion. So we're going to do a lot of calculations for things where the acceleration does stay constant. So, okay, not every motion has constant acceleration. But some important ones do. Of these, the most important is objects that are in free fall or projectile motion. Okay, so now I'm going to define some things. So let's define P sub I and V sub I. So those are going to be the position and the velocity when time is equal to 0. And so you can think of that as time equals 0 is when you click the stopwatch on. You start the timer running, you know. And then we'll define PF and VF. You know, I is for initial. That's why those I's are there on the first one. The F's are for final. That's why those have the subscripts F. PF and VF are going to be the position and velocity at time, I'm going to call it time t final. And that's when you click the stopwatch off to look at the value, you know, to see you've been timing this thing. That's when you look to see how long it took. Then here are the three equations. The first one says V final is equal to V initial plus A, the acceleration, times T final. The second one says position final is equal to position initial plus V initial times time final plus 1/2 times A times time final squared. And the last one says 2 times the acceleration times the quantity P final minus P initial is equal to V final squared minus V initial squared. So those are the three equations that we're going to use for constant acceleration. And I'm going to list out some steps for how to use these that you can refer back to. And then we're just going to do a few example problems like the rest of today and then probably a little next time too. So here are the steps for using the constant acceleration equations. Okay, so the first thing you have to do is you have to make some choices about how you're going to configure things in the real world. Okay, so this sort of connects the math to the real world. Oh, crash. So there are four things that we have to choose. First, we have to choose in the real world the location that we're going to call position equals 0. That's like your reference location. Then you have to choose in the real world what you're going to call the positive direction. And then you have to choose 2 times. You have to choose the instant that you're going to turn the stopwatch on. That's our time equals 0 instant. So that's like when you click on your imaginary stopwatch. Sometimes it's imaginary, sometimes it's actually like we will be taking these time measurements. And then the fourth one is we have to choose a time final instant. And that's when you click your imaginary stopwatch off. Now that you've made that connection between the math and the real world, now you can think out of this list. So this is the list of all the variables that show up in these constant acceleration equations. So out of time final, acceleration, P initial, P final, V initial, and V final. Figure out which one you're trying to solve and which ones you know, okay? So which ones you know, which one you're trying to solve. Once you've done that, look for one of those 3 constant acceleration equations that, so first of all, it has to have the variable you're looking for. I mean, if you're trying to use an equation to solve for a variable, it has to be in the equation. So look for the constant acceleration equation that has the variable you want. And every other variable in the equation is known. And again, that's just mathematical necessity. I mean, if you're trying to solve for a variable, let's call it v sub I, v sub I has to be in the equation, and every other variable in that equation you need to put a number into. Otherwise, you can't use a single equation to solve for two variables. It just isn't possible. And then the last one, most of the time you won't need this, but sometimes you will. So that's why it's in parentheses. This is sort of as needed. If no equation works, find an equation that lets you solve for either time final or the acceleration, and then just go back to step 2 again and try it again. Okay, so clearly these don't mean too much to you yet. We haven't seen how this all works yet, but as I go through examples, I'm going to try to be really clear about following these steps. And I think you'll be happy if you really make an effort, like even set these steps out beside you as you go through these problems, and just try to get into a habit of doing it the same way every time, you know. I think you'll find it makes it a lot easier to make sense out of all this. Anybody need more time to write this down before I go on? Anybody have any questions? Okay. Here's the first example. Let's say that a car is traveling at 40 meters per second and hits the brakes. And then we measure how long it takes from when the car hits the brakes to when it stops, and that distance is 30 meters. So the car stops 30 meters away. So first, let's figure out the car's acceleration as it's braking. So what's the car's acceleration? And then second, let's figure out how long it takes in time for the car to stop. And I'm going to start by just sort of sketching a picture of what's going on. So here's the car. And let's say that, so the car's path is this. And when the car is at this red dot, that's when the car hits the brakes. And then the car comes to rest here. And we're told that this distance is 30 meters. So When the car gets this red dot, it's at rest. When it's at this red dot, it's going this way at 30 meters per second.
Isn't it 40?
Yes, thank you. Okay, so the first step is in the real world, we have to choose what we're going to call our zero position and our positive direction. Okay. It turns out actually that these two choices, you can solve the problem no matter what choices you make of these two. You just have to be consistent through the whole problem, and that's why we're going to choose them. The two times, the two instants, you pretty much have to choose those correctly or you can't do the problem. Okay. And correctly with those times means you're picking those times at an instant where you're either trying to find a value or you're picking them at an instant where you know a bunch of values. Okay. Okay, so what do you want to choose as zero position? I think most people would probably choose where the car is when it starts braking. But let me do it a different way, just so you can see how it would work, you know, if you did it, you know, so you can see that you can make these different choices and still do the problem. So let me pick that my zero position is here, where the car is when it comes to rest. Okay, and let's say I'm going to call my positive direction the direction towards where the car hits the brakes. So positive is that way, negative is this way. That's kind of all backwards of what I would probably pick naturally, to be honest. But and now what about the instants? Well, we're going to have an earlier and a later instant, and they're going to be based on an instant where we have information already and an instant where we're trying to find information. Okay. So you can maybe sort of just do this intuitively and you'd probably be right. Our time equals 0 is going to be like, if you're thinking like of actually timing this braking, you would click the stopwatch on when the car hits the brakes, and then you'd click it off to look at it when it comes to rest. Okay? So our time equals 0 is going to be when the car hits the brakes. And our time final is going to be when the car comes to rest, you know, reaches rest. Anybody have any questions about those four? And now we're going to list out what variables we know and what one variable we're trying to find. And I'm going to just go through this list. There are 6 total variables in the equations, and I just always do them in the same order. So there's time final, acceleration, P initial, P final, V initial, and V final. And for part A, we're trying to calculate the acceleration. Well, do we know how long it takes? No. For part B, we're going to try to find that, but for now we don't know what it is. And we're not looking for it yet. That's part B. So I'll just cross that off. Do we know the acceleration? No, that's what we're trying to find, so I'll put that over here. Do we know the car's position at time equals 0? Do we know the car's position when we click on the stopwatch? We do, and you have to do that figure that out sort of the same way you did those position versus time problems from last week. So if you start at 0 and go 30 meters in the positive direction, what's the value where the car is here?
30 meters.
Yeah, positive 30 meters. So our PI is positive 30 meters. Do we know the car's position when it comes to rest, when we click the stopwatch off? Yeah, what's that?
0.
Yeah, we chose that at 0. Do we know the car's velocity when we turn the stopwatch on? Okay, so for this, be careful, because I chose these weird directions. We know that the velocity is plus or minus the speed, okay? The speed is 40 meters per second. And now you have to ask yourself, is it moving in the positive or negative direction? Yeah, the way I have it drawn, it's moving in the negative direction at that instant. So this is negative 40. And then do we know the velocity at time final when it comes to rest? Yeah, being at rest means velocity is 0. So there we go. And so now we have a bunch of variables we know. We have one we're looking for. We're going to go through the 3 equations that I gave you and try to figure out if there's one that has A in it. And everything else that appears in that equation is listed under what we know. And the one that works, I mean, let me just list them out one by one, and we just this one time, and we can just kind of think through whether it meets what we need. So the first possibility is V final is equal to V initial plus A times time final. Well, it does have A in it, so that's good. And now go through the other variables. V final, we know, so that's good. V initial, we know, that's good. A is what we want, but the problem is we don't know T final. Okay, so this one isn't going to work. It's not going to let us solve for A.
Oh, so you go through each one of the ones?
Yeah, that's the way I would do it for now. I mean, I think in a couple weeks it'll be kind of more intuitive, but for now, just go through and ask yourself, is this in there? Is this in there, you know? Then the second possibility is this one. PF is equal to PI plus VITF. And there's the problem right there. You know, it's the same issue we had before. We don't know what TF is. And so this one won't work either. So the last possibility is this one, 2 times A times the quantity PF minus PI is equal to VF squared minus VI squared. This one has A in it. PF we know, PI we know, VF we know, VI we know. So this one should work. And now we're just plugging those numbers in. And I listed all of my variables with their units. And it's actually kind of cool how it works. Like if you actually carefully kept all your units with your calculation and canceled the units as you went, your answer for acceleration would actually give you the correct units for acceleration. It's kind of a way to check your work, but it takes a lot of time and it's kind of tedious. So I'm not gonna ask you to keep the units, but it will work that way if you do it.
But what about for A? Are we trying to figure out A?
We're trying to find A, yeah, exactly. So I'm just gonna put in all the things we know, and then we're just gonna do the algebra to solve for A. So we have 2 times A times the quantity, P final is 0, minus P initial is positive 30. And that's equal to 0 squared minus V initial is negative 40. So minus 40 squared. And you do have to be a little careful here about the order of operations. We're going to square this negative 40, but we're not squaring the minus from the equation. So if I simplify this, we have 2 times a times negative 30 is equal to 0 minus negative 40 squared is positive 1600. So this comes out to be negative 1600. And now I'm just solving for a, so I have negative 60a is equal to negative 1600. Divide both sides by negative 60, and you get that a is negative 26.6 repeating meters per second squared. That's a huge acceleration. I don't really know if tires would hold onto the road that well, but yes. Thank you. Positive. Thank you. Anybody have any questions about that? Okay, so now we can do a little bit of sanity checking too, because we did this calculation and figured out that acceleration was positive. Okay. Let's look at this problem and figure out whether it makes sense that acceleration is positive, because clearly this car is slowing down, right? Remember that for something to be slowing down, the velocity and acceleration have to have opposite signs, okay? So throughout the motion of this car, what's the sign of the velocity? Negative, because of this kind of funny way I define positive and negative. So my velocity is negative, my acceleration is positive. That means that this car is slowing down, which is a good sign. Okay? Anybody have any questions about that? Yes?
For them a little bit.
Yeah.
When you figured out A, why did you put so the ending of it?
Yeah.
Where do we get it from?
The one in the box?
Yeah.
So you have negative 60a is equal to negative 1600, and so then just divide both sides by negative 60.
I know, I'm talking about for the equation of the meters and then for the units.
Oh, how did I get the units for that? Okay, so you could keep the units in everything and it'll come out right, but all I'm doing is I told you when I defined acceleration that SI units for acceleration are meters per second squared. So just put them on at the end. Yeah. Okay, now we want to figure out the elapsed time for this braking. So whenever you have multiple parts of a problem, ask yourself each time you start a new part, is there any reason that I need to make different choices for time equals 0 or time final? In this case, there's no reason to. The only reason you would have to is if the problem is asking you for information at an instant that isn't one of the ones you chose before. This doesn't have anything like that, so we might as well just keep what we have. So for part B, we're just going to keep the same position equals 0, positive direction, time equals 0 instant, and time final instant. And if you keep all those same 4 things, then everything you knew before, you still know. So I can go back up here and just list out all the things I knew before. Let's see. And now I know the acceleration too. We calculated that. So now I know that acceleration is 26.6, repeating. I want to find time final. My initial position is still positive 30 meters. My final position is still 0. My initial velocity is still negative 40. And my final velocity is still 0. And in this case, there are actually 2 equations that would work to let us calculate T final. So let's look at these 2 that'll work. We know we need to have an equation with T final in it, so the third one won't work for this, but this one will. And this one will too. Whenever you have the choice though, take this one. It's simpler. There's no square in it. You never end up having to go into the quadratic formula with this one. So always just take the simplest equation that'll work. Okay. And so let's just make sure that it'll work. Time final is in it, so that's a good start. V final is known. V initial is known. A is known. So this will let us solve for T final. Okay, so 0, V final is 0, is equal to negative 40 plus 26.6 repeating times time final. And so add 40 to both sides. 40 is equal to 26.6 repeating times time final. Divide both sides by 26.6 repeating. And you get the time final is equal to 1.5 seconds. And let me say one thing. The fact that time came out positive, never in this class should you get a negative time. Something went wrong if you get a negative time. So the fact that this came out positive is a good sign. Question?
Can you put the exact number, like in a fraction form?
Yes, sure, yeah. I tend to just punch stuff into my calculator and then just round. I'm always going to be grading you on tests and whatever based on the steps that you follow. And so you can round as much as you want or keep stuff as you know, in a keep stuff in fraction form if you want. I'm not really grading it based on the answer. I'm just grading on that you're following, thinking about it right. Yep.
It's kind of out there, but like, how long do you think something like this should be?
Oh yeah. Well, right now it'll take you a long time. You know, probably. I mean, it's going to vary a lot per person. Within 2 weeks, a problem like this will be really fast for you. But I wouldn't be surprised if doing a problem like this took half an hour right now. You know, but it won't feel long like that for very long. Yes.
Theoretically, and I know that usually we would have all but one variable.
Yeah.
Would you be able to do something like a piecewise function or like a substitution? Like theoretically.
Yeah,
the
yeah.
Two variables that
You can't do it with these equations. The only thing you can do is that kind of bootstrap thing where you can use one equation to find
Right,
T
the
final or
substitution.
acceleration,
Okay.
and then use another one to get the other thing. So I guess in a way that's kind of what you're talking about.
Okay. But,
Yeah.
but in this class, we would always have all but one variable, correct?
No, you will get some where you have to solve for T or A,
Okay.
but yeah. Any other questions? Okay, let's stop there, and I'll give you 1 or 2 problems like this to do for Wednesday, and then we'll just keep going with this. And also, so this is going to be probably for a lot of people a little rough at the start. If you have trouble getting through something, don't worry about it. Let me know. I'd be happy to go through these problems on Wednesday. We're really just going to be doing example problems for a little while now. Okay.
Thank you.